Hi, so welcome back to Math 140, Calculus 2. This is lecture 19. So as I was telling some of you before class, I think this is the hardest lecture of the semester because this is now shifting gears from being on break to coming back. I know, of course, you've been doing nothing but math, well, almost nothing but math, the last 2 weeks, but it hasn't been in the class. That's why it's not quite the same. So what I want to do is I want to first use some of today to just talk about whatever topics anybody has any questions about. Is there anything people want to review before we then go on and start talking about sequences and series? So are there any topics from the semester so far that people want to discuss? I would probably then choose maybe a problem to just discuss, to just review some calculus as well. How many of you have ever done the drowning swimmer? All right, so if you are a lifeguard and there was a drowning swimmer, what is your objective? To save them, right? If I ask you, you own a company, what is your objective? To make money. There's a lot of questions where the objective is clear. What's less clear, if you're a lifeguard, is how do you save the drowning swimmer? Well, I subcontract out. No. How do you save a drowning swimmer? You swim after them. Okay. So let's imagine we have here is land, and here's the water. And I am not going to even bother trying to draw the swimmer well. Here's my poor swimmer in the water. Here is my lifeguard. How does the lifeguard get to the swimmer? We will assume for simplicity that there is no one else on the beach. Is this a reasonable assumption? Not necessarily. And if there's people on the beach, what might this do? Cause chaos. So what could that force you to have to do? Maneuver around. So there was a medical accident in the science building maybe a week or two ago. And so a couple of us immediately stepped up. I called 911, someone else called campus security and whatnot. And so 911 dispatched an ambulance. And I went downstairs and I used my professor's voice. I need students now. And I got several students to come with me and said, your job is you keep the elevator door open. So as soon as the ambulance comes, they can get in the elevator, go straight up. You hold this door open so as soon as they can come in, you keep the path clear. And we just had enough students down there so that fortunately everybody was okay. It wasn't time sensitive. But we were able to just put people in position. So God forbid, seconds mattered. We had the whole path clear. It becomes a more interesting problem if you have officers. We'll assume there's nobody in the beach. How should how should the lifeguard get to the swimmer? What path should she take? So one possibility is the straight line. Can anybody think of another path? So we will assume that there is no current. So go straight up like this, and then go like that. So go like this. I'm sorry. Go like this. Yes. Right, so there's a lot of implicit assumptions. We will assume that the lifeguard runs faster than she swims. Going straight up and then swimming is actually the worst thing you can do if you're not a complete moron. The complete moron is kind of spiral like that. We will assume the lifeguard will not do that. The lifeguard is going to choose some point on the land-ocean boundary and run straight for that point, and then from that point onward, swim straight to the swimmer. So the lifeguard's path is going to look something like this. And we have to figure out where is that point. Okay? Now, one possibility is to just run straight. Another possibility is to run as far as you can diagonally so that you're just underneath the swimmer and then go straight. That minimizes your time in the water, maximizes your time in land. So can somebody give me a reason why that might not be the best thing to do? I mean, that seems pretty good. Spend as much time as possible on land where I run faster than I swim. Let's imagine some extreme, I love extreme situations. Let's imagine you run at 10 miles an hour. Do you think you can run at that speed? Is it at least humanly possible, 10 miles an hour? It's a 6-minute mile. You know, I'll assume that we can, and let's assume we swim at 9.999999999 miles an hour. I don't think we can swim that fast, but let's assume we can. If that's how fast we swim and that's how fast we run, do you think that the best path would be to go straight under? What do you think the best path would be, or would be close? Why would it be close to the straight line?
Difference in your swimming and running so small, it doesn't matter. Like, it doesn't make a difference that you run the extra distance on the
Good. Good. What's the real problem? If we take the route where we go directly under the swimmer, we are doing what? It's much more distance. And so the small increase in speed is not worth it. So it makes sense that where you're going to go depends on the relative speed of how you are in the water versus land. So again, I don't particularly care about this. I have talked to family members and friends who are lifeguards. Nobody ever does the calculus. They just run straight to the swimmer, which is much better than just stopping and doing the calculus at the moment. Do I add one or subtract one to the exponent? You should actually do the calculus beforehand. And so if the swimmer's here, I know exactly how I should be running. So it makes sense that the path is going to be a function of the relative speed between land and water. As you run faster and faster on land, let's say you run almost infinitely fast on land. Now this of course violates special law. Let's assume you're running 186,000, maybe 185,000 miles per second on land. At that point, yes, I will basically run directly under the swimmer. So this simple analysis shows that as we vary the relative speeds, where we run should also vary. It should be a function of where we go. You want to try to figure out what are the key parameters. How fast does the lifeguard run on land? We need to choose a bunch of quantities. How far is it on land from one point to the other? Nope. I can make things nice. I assume it's what distance? 1. It's 1 unit. Right? Here's 0, here's 1. It's 1 unit. Once I choose that, I have no freedom now in terms of how far into the water the swimmer is. Whatever that number is, it is. Right? So maybe I'll call the distance over here maybe YL for land and YW for water. And the lifeguard is going to swim, so is going to run to some point X. So 0 less than equal to X, less than equal to 1. How fast does the lifeguard run on land? Can anybody tell me what unit of measurement a furlong per fortnight is? Really? A furlong per fortnight. So it's something every 2 weeks, good. So you know that the denominator is time. A horrible unit of time, but it is time. What is a furlong? Does anybody know what a furlong is? If you think, what might be something per time? Distance. A furlong is a measurement of distance.
What's this like? Okay.
A furlong is 1/8 of a mile. Yes. It's been a long time since I've used that unit. So a furlong is 1/8 of a mile. So 1/8 of a mile per 2 weeks. This is a horrible unit of measurement. The only time I've ever been able to use it is, the building has been going up at so many furlongs per fortnight. Something really strange. You can use that as a unit of measurement. Is there somebody here who's interested in astrophysics? the distance from the Earth to the sun is about 90 million miles on average, or 1 astronomical unit. And for a lot of things, it's more convenient to just talk about it's 1 astronomical unit. I can choose my units of time and distance. So what is my lifeguard speed on land? What's the speed on land? I can make it what? I adjusted it so that the horizontal distance was 1. I'm trying to keep the numbers as simple as possible. What can I assume the speed is on land? 1. Yeah, I choose my time unit appropriately so that the speed on land is 1. And then the speed in the water is VW for the water speed. Okay. And so now I want to figure out where the lifeguard should run to minimize time. So this is a nice way to review a lot of calculus. 0, x, 1, v water, and y water, y land. I just want to try to make it look really clear that there's some kind of bend here. And its speed is 1 here, and the speed is VW here. So how long are you on land? What's the land distance? How long are we on land? What's the land distance? So x squared plus YL squared. And so the land time is what? I have my distance, and I have my speed is distance per time. So how would I get distance divided by speed? So it's the square root of x squared plus YL squared over 1. I am going to write the over 1. I'm going to drop it very soon, just so we see how we're getting it. What's the water distance? So we have another right triangle. So it's going to be the square root of 1 minus x squared plus YW squared. And the water time is going to be the square root of 1 minus x squared plus YW squared over VW. And so we want to minimize, let's call it T of x, which is the square root of x squared plus YL squared plus the square root of 1 minus x squared plus YW squared times 1 over VW. Subject to 0 less than equal to x less than equal to 1. So how do we find where a function is largest or smallest? Trying to review some calculus. How do we find where we have a maximum or a minimum? So I said 0 equal to 0. Anything else? Yes, did I run into the door in this class? All right, so tell me where my speed is largest. Yes, actually not right before. As I was hitting this. It's not enough to check critical points. Pre-COVID, I would have just kept the door closed for the rest of the class. In the COVID era, I will open it for air circulation. And I'll give my hands just a chance to. So it's not enough to check where is your first derivative equal to 0. That finds critical points, that's candidates. So when you're looking into an interior max or minimum, the first derivative has to be 0. If the first derivative is positive, well, you're going to be a little bit larger a moment later, and you were a little bit smaller a moment before. The reverse is true if your first derivative is negative. So if we're looking for an interior maximum or minimum, the first derivative must be 0. Why doesn't that hold at the endpoints? Yeah, there won't be both the before and after. You know, if you're at the right endpoint, there is no after. So my first derivative is positive, so what? I can't go forward one moment in time. There is a physical stop in terms of the time. And so we have to check the endpoints. Now, when we look at this, it turns out one of the endpoints is going to be very easy. You know, we will assume that VW is less than 1, that the lifeguard swims slower than she runs. So clearly, x equals 0 is bad. So x equals 0 is bad, x equals 1 in the running. Okay, so now we have to differentiate this function. And we have to evaluate it at 0 and also check the critical limits. So what would be the derivative? So t prime of x would be, take the derivative, so it's going to be 1/2, and we'll have x squared plus yl squared to the to the 1/2 down below. And then the derivative is going to be a 2x, right? So the 2's will cancel, right? And for the next one, it's going to be 1 over VW. We'll have a 1/2. We'll have a 1 minus x squared plus yw squared to the 1/2. And now when we take the derivative, it's going to be 2, 1 minus x, and then a negative 1. And the 2's cancel. Okay, so t prime of x equals 0 means x over x squared plus yl squared to the 1/2 equals 1 minus x over VW 1 minus x squared plus yw squared to the 1/2. So is everybody comfortable with how we got to this point? Now what do we do? We've got to solve for x. Remember, VW is known, YW is known, YL is known. There's only one unknown. So we have to solve for x. How do we solve for x? Does everyone agree that this is a nightmare? What's making this hard for you? What do you hate the most? Okay. That's not what bothers me the most. If there were just x's in the numerator and denominators, I wouldn't be too upset. Yeah, there's a square root. How can you get rid of the square root? Square. Now, when you square, you run the risk of introducing extra roots. As an aside, if x equals 1, what can you solve for x? This is the most softball question I can give you. Yes, what would x equal if x equals 1? 1, okay? This is the type of question you ask a politician if you want to write a fluff piece on them and avoid anything that might make them feel uncomfortable. Right? Well, I'm going to solve x equals 1 as follows. I'm going to square both sides so I get x squared equals 1. And I subtract 1 from both sides. I factor this as x minus 1, x plus 1 equals 0. So x equals 1 or minus 1. So the solution to x equals 1 is x equals 1 or minus 1. Is minus 1 a solution? So what happens is when you square, you can introduce phantom roots. So can have phantom roots from squaring. So we have to be careful, but let's square. And let's also cross multiply. And then we'll clear the denominators. So we would then get x squared times VW squared times 1 minus x squared plus YW squared equals 1 minus x squared times x squared plus YL squared. So this is what we get if we square and cross multiply. Okay. What kind of polynomial is this? So what kind of polynomial would this be? It's a fourth power. If you look at the left, when you multiply everything out, you're going to have an x to the fourth as the highest term. If you look at the right, when you multiply everything else, it's a fourth order. So this is a quartic. There is a formula to solve the quartic. I think we talked about Newton's method earlier in the semester. So we actually have a way to numerically approximate roots. Okay. What I love about the drowning swimmer is this is a real world problem. How do I get from one point to another as fast as possible? Traveling in two different media. And the solution not only uses calculus, but now I have to solve a polynomial degree 4. There is a formula that you can appeal to, or you can numerically approximate it very quickly using something like Newton's method. Is there anybody here who's taking physics or has taken physics? Does this remind you of anything? So you have something that bends as it passes from one medium to another. It's, yeah, so this is your Ni and your Nr. This is, Snell's law. It's been a while since I've done this, but what path does light take? Light takes the path that gets it from one point to another in the shortest amount of time. And the speed of light does change depending on what medium you're in. Where is light traveling fastest? What medium? So it's a vacuum in space. And as light goes through a medium, it goes slow. And so you have a bending like this in physics. And one way to view a lot of physics is there's a lot of these minimization principles that the paths particles take are the paths that minimize either the total time or what's called the action for something. But getting back to what we're trying to do now, we have this wonderful equation that we need to solve. So what I want to do now is, this is the 21st century, right? We should be doing things not on your pen and paper, but we should actually be using the computer to do things. And so what I want to do is, here are the two different functions, the time function and the equation we need to solve to find the critical time. So let's create a function. So t of yl, yw, and it's a bw, underscore in mathematics to say that it's a variable. It's going to be x squared plus yl squared plus squared plus YW squared divided by VW. So let's do a plot of X. We have to choose values for YL, YW, and VW. Do you want to do it's the same distance from land as it is from the water? The lifeguard has the same distance. Your VL equals VW. I mean, YL equals YW. So we'll do that. We'll say maybe 0.3 for both of those. And then how much slower do you think the lifeguard is in the water than on land? Okay. I think that's generous, but we will have a buff lifeguard who can do that. And I'll plug it. And so this is basically telling you, if I plot the time, you're looking at this, this is about where I should be. Now, one of the things I truly love about Mathematica is the manipulate function. So what I'm going to do now is I'm going to put in here VW. It's going to go from 0 to... Do you think I should allow VW to be 0? Why not? You can't move in the water then. If I were to run this, what should happen? You would never get there, right? And so it should probably crash. So I will risk crashes, right? Infinite expression you can't do. It's not happening. So let's change it to 0.01. And now you can see what's going on with the time, and I can change the speed. If I do the here, I can increase, and you can see how it's falling down, and you can see the point is changing. Where do you think it's going to be when the speed in the water eventually hits 1? The same speed as land. What do you think X should be in that case? 1/2, because I chose it to have the same distance in both. And so we can see, oh, it looks like it is converging, and it converges to 1/2. So this is doing a very special case. Could we add more manipulations? Absolutely. We could manipulate also the distance from land to the lifeguard and the distance from the water to the swimmer. So you could just put in more things. So if I wanted to, I could replace this 0.3 and I could add something else there. So this is something you really want to be able to do to explore dynamically what's going on and just get a sense of what's happening. You want to have some intuition before you even do any calculations. So one of my cousin's children's girlfriends called me up with an Algebra 2 question. And you had $7,500 in the bank, 13% interest. How long would it take to get $10,000 compounded continuously? And so before we even did the calculation, we did some estimates and we said 5 years is too much, 1 year is too little. I would guess at most somewhere between 2 and 3 years. The teacher's answer was 70 years. And so this is why the person was a little bit confused as to how did you get 70 years? It turned out the teacher just forgot one of the numbers in the problem and just did the algebra wrong. But you should have some intuition. It shouldn't take me 70 years when I'm getting more than 10% interest a year starting at $7,500. You should have some idea of what the answer looks like. And again, that's what I really want to emphasize in this class. This is why we're not rushing to get through a tremendous amount of material. That's not the goal. If you need any of this material, you can pick up what you need. And to some extent, as you go further and further, you need to do less and less of this because people are just having the computers do the calculations. You need to understand what calculations do you want the computer to do. So how do we set up the problem so that the computer can do that? Now, the next one is, we want to actually find the critical point. So I'm going to just copy this down below so I can see it again. So I'm going to let time of x. It's going to be a function of not just of x, of dw. Let's see what was used. YL, YW, and VW. So it'd be x squared VW squared minus x squared plus YW squared. So please make sure I'm not making any mistakes. Minus 1 minus x squared plus YL squared. Correctly? No typos. All right, so now what we want to do is we want to solve for that equal to 0. So let's numerically solve time of x. I think we do 0.3, 0.3, and 0.5. 0. And so we get 1, 2, 3, we get 4 roots. Does that surprise you? Why not? It's a quartic. The first 2 roots are complex conjugates. Okay, I don't think a swimmer is going to be saved by a lifeguard running to a complex position. The 4th root is actually greater than 1. I love that. Right? We're somehow overshooting and coming back. Now, if there was a current, could that be reasonable? Yes, if there's a really strong current and you run fast on land, it might actually make sense. And that becomes a really interesting problem, which I'm not sure if anybody has looked at. So email me to see if anybody has looked at a modification of the drowning swimmer with a current, where this could be a really good example of you overshoot and then come back. And then there's one answer that looks reasonable, 0.839. Well, if you look at what we had before, so we initially were having the swimmer at 0.5, I think. Yes. Does it look like 0.839 could be reasonable? We could zoom in on this if we wanted to. Probably the cheapest way to just zoom in. Yeah, 0.839 seems reasonable. How much is each dot? Basically, each dot is maybe about 0.25. So ballpark 0.839 is definitely seeming reasonable. All right. So this is the drowning swim problem. Let me just put this into the notebook. Okay. Any questions about the drowning swimmer? So to solve it, for all possibilities is going to be, a lot of work. What you can do is you can solve it for special cases. You can get, some intuition about what's going on. Okay. So what I want to do now is I want to turn to, starting to do some of the sequences and series tests. So it's debatable as to whether or not you cover this topic in Calc 2. I think it's one of the topics that's really worth covering, because so much of what we do in later math and science classes is we take something complicated and we try to replace it with a bunch of simple things that we understand. And if you're going to do that, you need to be able to show that the simple things you understand, that they converge to something nice, hopefully to whatever you want to study. And this is where we get the subject of Taylor series and approximations. We've already seen approximating a function by a tangent line is locally a very good idea. And then if we do a parabola rather than a line, it should hopefully do an even better job. We talked a little bit about this with techniques of integration. When you want to numerically integrate something, the simplest is left endpoint, right endpoint, and that gives you rectangles. Then there was the trapezoid, which used the left and the right endpoint and made a trapezoid. Then there was the Simpsons rule, which used a parabola going through those two and the midpoint between them. And so, not surprisingly, the better shape you use, for the most part, the better job you can do. I'm smiling because if I know what method you're using, I can probably construct a function, if I know how many subdivisions you have and what method you're using, that will be very bad precisely for what you're using. But if you then change the number of points a little bit, then you would probably be good again. But most of the time, a parabola will do a better job than a straight line. We talked a little bit about the product rule for derivatives, in the before spring break, and we said we knew that the product rule sadly was not going to be the derivative of a product is the product of the derivatives. And we took some simple functions, x to the n, x to the m, x to the n plus m, and we were able to calculate the derivative of all three pieces, and we were able to conjecture, hey, maybe the derivative of a product is f prime g plus fg prime. And we saw that worked for any finite polynomials. This is a big idea in mathematics. Start small, prove it there, build up. And so we first said, well, look, if it holds for two functions, it holds for a multiple of one of them, it holds for the sum of them, so it holds for any finite polynomial. And then does it hold for an infinite polynomial? And that gives you now some idea of why I might care about proving these results about convergence of sequences and series. Because I want to replace complicated functions with sequences and series. You've already seen sequences and series for functions. So some of you might remember, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And that's just the sum of x to the n over n factorial. It turns out that cosine of x and sine of x, the way we really evaluate them is we give infinite series. So this is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. This is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And it turns out e to the ix is cosine x plus I sine x. And this is e to the ix plus e to the minus ix over 2. This is e to the ix minus e to the minus ix over 2i. So we might talk more about this later in the semester. But this is why I'll risk saying this. Do you remember your angle addition formulas from trig? The sine of x plus y is sine x cosine y plus cosine x sine y. And this cosine x plus y is cosine x cosine y plus minus sine x sine y. These angle addition formulas actually come from the exponential function. E to the a plus b is e to the a, e to the b. The reason sines and cosines have these angle addition formulas is they inherit them from the exponentials. So this is another reason why we might care about sines and cosines, or why we might care about sequences and series and convergence, is the way we understand sine and cosine is these are infinite sums, and we need to know these infinite sums converge. Okay, so we talked a little bit, I think, last time about the geometric series. The geometric is our go-to series. So geometric, so the nth term is a0 r to the n, and then a0 plus a0r plus a0r squared plus a0r cubed plus dot 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 is equal to a0 1 over 1 minus r if the absolute value of r is less than 1. So this is the famous geometric series formula. And it is one of the most important formulas in all of mathematics. There are very few series that we can evaluate in closed form. This is one of them. What's really nice about a geometric series is if you chop off the beginning of a geometric series, what's left is a geometric series. So if I look at, for instance, a0 r to the 5th plus a0 r to the 6th plus a0 r to the 7th plus dot dot dot, that's just a0 r to the 5th, 1 plus r squared plus dot dot dot. This is a geometric series. It's very rare to have something like that, where if you throw away, a couple of things in the beginning, that what's left over has the exact same functional form, just like a rescale or a reshift. So we know a geometric series converges if r is less than 1, it diverges if r is greater than or equal to 1. And the goal is to try to figure out when does a sequence or series converge. So I think we talked before break about necessary versus sufficient condition. So can you give me a necessary condition for a sequence to converge? So necessary for the sum of an and goes from 0 to infinity to converge. What must be true about an? It needs to go to 0. If an doesn't go to 0, it's not going to converge. This is not sufficient. And for example, I could do 1 plus a half plus a half plus a third plus a third plus a third. Hopefully the pattern is clear at this point. This sequence is not going to converge. Even though the terms are going to 0. So whenever possible, you always want to try to find extreme cases to play with to get some feeling for what's going on. And this is enough to show us that it's necessary for an to go to 0, but it's not sufficient. So if I had to describe mathematicians with just one word, I would probably use the word lazy. Whenever possible, we want to avoid doing hard work. So before trying to figure out, does a series converge, let's do the easiest test possible. Do the terms go to 0? If they don't go to 0, there's no need to do anything further. If they do go to 0, then we're in great shape. We have at least a chance of having convergence. Then we start to use more powerful tests. And so we start to have some tests that some of the ones you're supposed to look at. So we have the ratio test. And so let rho equal the limit as n goes to infinity of the absolute value of an plus 1 over an. If rho exists and rho is less than 1, it converges. Greater than 1, it diverges. Equals 1, we have no information. So this is the famous ratio test. So long as you can calculate this limit, you can tell if the series converges or diverges, if you're lucky. If you're not lucky, what value would you get? So if you had an evil professor on an exam, what value would you get? One. Because if you get the value of 1, you don't know if it converges or diverges. So for example, let's let an equal 1 over n. This is the harmonic series. It turns out this series diverges. So we have 1 plus a half plus a third plus a fourth plus a fifth, sixth, seventh, eighth, ninth, and so on. And what I'm going to do is I'm going to break it up like this. What's the sum of 1/2? 1/2. So this is greater than or equal to 1/2. And the sum of 1 is just greater than or equal to 1/2. What about 1/3 plus 1/4? What is that greater than or equal to? 1/2. Because 1/4 is the smallest of the two terms. So this is greater than or equal to 2/4, which is 1/2. What about these 4 terms? What's the smallest of the 4 terms? It's an 8. So this is at least 4/8, which is 1/2. This is at least 8/16, which is 1/2. So we see that as we go further and further down, we're always going to be adding at least 1/2. So even though the terms are going to 0, the series is going to go off to infinity. Yes?
Does the number of terms being grouped together just double every time?
Yes. Yep. So we're just doing powers of 2. Now let's look at the limit as n goes to infinity of an plus 1 over an. This is the limit as n goes to infinity of 1 over n plus 1 divided by 1 over n. That's the limit as n goes to infinity of n over n plus 1. What does n over n plus 1 go to? 1. You know, a million over a million and 1, a quadrillion over a quadrillion and 1, it's going to go to 1. So here's an example where rho equals 1, but diverges. So I want to show you that there's an example where rho equals 1 and it diverges, and there's an example where rho equals 1 and it converges. Okay. The rho equals 1 is a little bit hard. We could try the sum of 1 over n squared and goes from 1 to infinity. This is easier if we know calculus. We have 1 plus a 4th plus a 9th plus a 16th plus a 25th plus . If we look at rho, which is the limit as n goes to infinity of an plus 1 over an, this is the limit as n goes to infinity of 1 over n plus 1 squared over 1 over n squared. This is the limit as n goes to infinity of n over n plus 1 squared. What would that be? So what's the limit of n over n plus 1 squared as n gets larger and larger and larger? 1. You know, we have a million over a million and 1 squared. Okay. I'm only raising it to a fixed power of 2. This is still going to be 1. So rho equals 1, but can show this converges. So we've got about 2 minutes. I'm going to show you that it converges using just elementary algebra, which is going to be painful. And this will then motivate why we're going to learn the integral test in the next class, because we're going to see how much better the integral test is. So let's look at the sum of 1 over n squared. And we're going to write this as a sum. K goes from, say, 1 to infinity. And then it's going to be 1 over 2 to the k squared plus 1 over 2 to the k plus 1 squared plus ... 1 over 2 to the k plus 1 squared. So I'm going to break up terms from, say, 1 over 2 squared to 1 over 2 cubed squared. Then I'm going to go from 1 over 2 cubed squared to 1 over 2 to the 4th squared. I'm going to keep breaking up. When I look at all of these terms, which is the largest term? It's the first, right? Do we agree that the first term is the largest? So this is going to be less than or equal to the sum. K goes from 1 to infinity. I have 1 over 2 to the 2k. How many terms do I have? I have 2k terms. So this is just the sum. K goes from 1 to infinity, 2 to the k over 2 to the 2k. That's just the sum. K goes from 1 to infinity of 1 over 2 to the k. What kind of series is that? What series is this? Geometric. This is just equal to the sum. K goes from 1 to infinity of 1/2 to the k. Geometric. R is less than 1, converges. All right, so I'm going to stop here. We're going to see a simpler proof of this. Really pause and go through this if you want, as to how you can prove that this converges. But this shows us that we have to be careful when you get no information. It really is no information. All right.